Hi everyone, in this video I want to dive into Hyper-V, which is something 15 years ago when it first came out, and for quite a long time I spent a huge amount of time in learning and helping my customers with, but obviously with Azure it's kind of got a little bit left behind in terms of attention, but realize Hyper-V still is the hypervisor used for Azure and Azure Local, and indeed part of the Windows Server offering. And with some of the things happening in the world and other hypervisors today and other offerings, more customers are looking back at their on-premises virtualization requirements. And so it made sense to sort of dive into what is Hyper-V, what sort of hypervisor is it, and some of the capabilities. Now, looking at when we have a physical box. So if I think about physical hardware, there's various attributes of that. There's things like the CPU, like doing the work. We have memory. Then we have things like network interface cards. And those network interface cards have some connectivity to various networks. We might use VLANs to segment that up. We have some kind of storage. Now that storage could be local in our box. Or again, this might go and connect to things like a storage area network using iSCSI or Fiber Channel. It might be connecting to a NAS or an SMB file share. We may also have GPU resources. That's obviously becoming a bigger and bigger thing today when we look at machine learning and how those GPUs can be leveraged for that purpose. So all of this kind of lives within a particular hardware box. And obviously on this particular hardware box, we could just install a single operating system. It could have a single purpose. But people ended up saying, well, we don't like that because we end up with a lot of wasted resource. It's very difficult to have to go and provision a whole box just for an operating system. You get a lot of wasted resource. You get a long time lag. And so people wanted to virtualize the hardware. And that's the key point of what we're doing here. With virtual machines, we're virtualizing the hardware to create these virtual sets of hardware. So if I now go up a level and think about, well, what is a virtual machine? We create one or more VMs on this piece of hardware. So I'll just create my VM2. Let's say we've got multiple virtual machines on this piece of hardware. And we allocate to each of those virtual machines a portion of the resources of that underlying host. So it would get a certain amount of CPU. It would get a certain amount of memory from that underlying box. We would also typically create some kind of virtual network interface. So it could go and connect to actual networks via the host connectivity. And we'll give it some storage. And again, that storage is going to be leveraging the storage of the underlying host typically. So it might be local storage, it might be storage on a SAN, on an SMB file share, whatever that might be. But each of these are completely isolated at a kernel mode level. They're not sharing anything in terms of the operating system. They're completely self-contained. Into this virtual machine, I would then install an operating system. It could be Linux, it could be Windows, it might be Windows Client, whatever I want. It would have on this storage, it would install the operating system, have its bootloader. It's showing it a virtual BIOS or a virtual UEFI, depending on the specifics of what I'm doing. But it's completely isolated from any of the other virtual machines. So it gives me now that ability to have multiple different workloads completely isolated on a single piece of hardware. And this was a huge deal back when virtual machines first started. And obviously, it's still a huge deal today. If you look at Azure and virtual machines, this is what it's doing. You have the host in Azure. And when I provision a virtual machine and start it, well, this gets instantiated on a particular host. And it allocates these resources from that underlying host set of capabilities. Now, what's enabling this sort of allocation and partitioning of the resources is the hypervisor. And when we think of, obviously, this is about Hyper-V, Hyper-V is Microsoft's hypervisor that initially, I think it was part of Windows Server 2008. I've still got my little Hyper-V can, which was Windows Server 2008. This gave you amazing Hyper-V energy, that a cool little robot mascot. But the hypervisor sits directly on the bare metal. And this is a really important point. So when I think of Hyper-V, Hyper-V is sitting on the bare metal. So it's sitting right here. And this is my hypervisor. So the key point about this is a type 1 hypervisor, just like KVM, just like VMware. It is not running on top of Windows, which maybe gets a little bit confusing because you think, wait, I enable it through Windows, but we'll get into that. So it's a type 1 hypervisor running directly on the hardware, just like all of the major hypervisors. It was part of Windows Server 2008. It's continued to evolve. It also leverages other components of Windows Server, like failover clustering is a key part, gives me a lot of the capabilities for resiliency if I'm using Hyper-V. And this is the same hypervisor again. There's not just Windows Server. If I'm using Windows 10 or Windows 11, I have Hyper-V in that. Azure is using the same hypervisor. It's using Hyper-V underneath. And so I mentioned that, well, when I use Hyper-V, I enable it via Windows Server. In fact, if we jump over super quickly, and if we were to look at our server for a second, this is my Hyper-V box, and we're looking at adding roles and features, well, the way I install this is it's a role. I say, hey, look, there's Hyper-V. So it would make you think, oh, this gets installed on top of Windows Server. But that's not actually the case. So when you enable Hyper-V, what it actually does is it changes your boot process, and you'll see this hypervisor launch type to auto. So what actually happens now is the first thing that happens is it loads Hyper-V directly onto the physical hardware. And then the Windows OS that you previously installed on the bare metal then sits and runs on top of that actual hypervisor. So it's kind of an important thing to understand that that is the structure of what it's doing. And so that Windows Server instance you had previously installed, that becomes the parent partition. If you think about it, well, the hypervisor is great, but it's very thin. It's primarily responsible for the compute aspects governing sort of CPU memory. And so the instance of Windows I had installed on the hardware into which I then enabled the Hyper-V role, well, that has a bit of a special function, but what it becomes is that management, that parent partition. So now I'm going to draw it bigger just because I want to draw more stuff into it. But the reality is it's very lightweight. I can make this a server core, so it can have less components if I want, or it can be desktop experience. It's really up to you, whatever you want. But it becomes this parent partition. When it's talking, it also is being allocated certain amounts of CPU, certain amounts of memory. It's still going through that hypervisor. But here's one of the key points, though, when I think about this. Imagine all of the resources we talked about for a second on this physical piece of hardware. So what is this parent partition used for? Well, we know we have the CPU and memory, and that is going always via the hypervisor. That is what is doing that virtualization of the compute. That's its key purpose. But then if you think about all these other types of hardware you have network drivers and storage drivers and GPU drivers. I don't want those sorts of drivers installed in the hypervisor. And so what this parent partition does is it's actually running the drivers, the ISV drivers, and it does the communication for the other child, for all the virtual machines on their behalf. So that's one of the big purposes of this parent partition. And when you look at hypervisors, there's kind of a monolithic and a microkernelized, which is really just about where do you run this parent partition? Some hypervisors kind of run it within that hypervisor partition itself. What Windows does is it actually puts it in a separate partition for an additional, in a way, think of a security boundary. It's another security boundary. Because realize this does more than just virtualization functions, it does management functions as well. Hey, I want to stop and start virtual machines. And so Hyper-V is a micro-kernelized hypervisor. It's a type 1, but it doesn't run the drivers inside the hypervisor. Because think of the scope of hardware Windows supports. It runs those ISV drivers in, again, a separate partition from that hypervisor. So that's a big part of it. And again, you can make this server core, which is just a command line interface. You can make it a desktop experience. There used to be a huge push to make it server core in ye early days. They've kind of moved away from that. Microsoft have. It's more about your choice now. You do whatever you want. You can have desktop experience. You can have server core. Most of the management you're going to want to do remotely anyway, but it's whatever works better for you as an organization. Now, if you look at this picture then, and I just said, well, when I talk about network and storage and I can virtualize GPUs as well, how then do they actually go and communicate through? So what we have is something called the VMBus. This is a kernel mode in memory, basically, which means basically zero latency bus. And so I can think about inside these virtual machines, well, you would have things like the virtual drivers. Then you have this VSC. So what's happening here is this is the virtual service consumer, and that would be in all of these virtual machines. And then it has an instance of the VMBus. And that VMBus then goes and talks to the VMBus inside the parent partition. And there's a unique for each of them. So obviously there's a VMBus over here. So it's that in-kernel stack. And then what it does inside the parent is it then has the virtual service provider. So then I have the VSP, which talks to the I/O stack, which then goes and talks to the actual drivers. So this is the structure of how the hypervisor parts work together. So the CPU and memory, that always goes directly just via the Hyper-V hypervisor. For the storage, for the network, for the virtualized GPUs, for other things, I don't want the drivers in the hypervisor directly. So that's what the parent partition does, and it uses this kernel mode in-memory bus to facilitate adding no latency to the operation. It just goes and flows through into that. So that's one of the huge parts of what this actually does. Now, when I think about the various components that actually make this up and the types of requirements we have on here, realize that I'm drawing all of these pictures. But ordinarily, if I think of a processor, there's various rings. There's like a kernel mode, ring 0, and the user mode, ring 3. And I still have all of those things happening. So I can think about at an OS level, I have this idea of, well, I have kernel mode. So kernel mode is this ring 0, which is where kind of all of these are. And then I have a ring 3, which is this user mode. But if the guest virtual machines can use ring 0, how can the hypervisor then manage those and give control? So this is why you actually, in the modern processors, you basically have a ring -1. So this is a special ring, and this is why we need the processors to be like AMD V. I think it's the Intel VT. There's other requirements you have. There's things like second level address translation. There's various data execution prevention capabilities. But this is what Hyper-V uses. So you can actually go and see the various requirements if we jump over. So you can see, hey, yes, so the processor has to have support for the secondary level address translation. This helps offload the memory mapping. So the hypervisor management tool doesn't have to be worrying about that mapping of the virtual memory to the physical memory. And then you can see, hey, it needs that hardware-assisted virtualization. So it talks about, hey, yeah, the Intel VT, the AMD V, and any modern processor just has this. This is not a problem today. Everything you're ever going to deal with is going to have those capabilities. So I don't think you can even get a processor that doesn't have that today. But again, because it's a type 1 hypervisor, it's using those capabilities to sit even below the kernel mode. So the guests don't have this ring compression where they're actually getting fake rings. They see the full scope of ring 0 to 3 within the guest. And the hypervisor is sitting even underneath those because it's a type 1, directly on the hardware, and it can still manage those things. Now, I mentioned this parent partition does more than just handle the drivers. If you think about, well, I need something to actually overall manage all of the virtualization. So there's a virtual machine management service runs in here. And then for every single virtual machine, there is a VM worker process. And that's a child process, I think, of the VM compute process. And that's responsible for monitoring the state of the virtual machines, for stopping and starting it. And you can see these processes, but that's obviously another thing the parent is doing. It's facilitating that management. So if we jump over to our hypervisor again, and what I'm going to do this time is I'm going to load up Process Explorer. Now, what I have on this box, I have 3 virtual machines running. So we can see those 3 running. So there should be 3 VM worker processes. And if we look at our Process Explorer, sure enough, let's just get rid of that a second. I can see I've got my virtual machine management service process. And then as children of the core VM compute process, I have my 3 VM worker processes, 1 for each of the virtual machines. And you can actually tell which of these worker processes is for which VM because it calls the GUID of the particular virtual machine. And if you were then to just go and look in the VM folder for the virtual machines, well, I can see the GUID. That's the sort of configuration file. So I can see that first process I was looking at is for that particular virtual machine. So you can always work out which is which. And then I have 3 VM connects because I have 3 console level connections on this box to my 3 virtual machines. And so that management partition, as we can see, is doing other things as well. Yes, it's responsible for handling the driver and the communication to the non-CPU and memory, but it also is responsible for stopping, starting, monitoring the state. And it's for that reason I can't reboot the parent without shutting down the virtual machines or saving their state, because a VM can't run if there's no storage or network connectivity anymore. So that's why, hey, when we have to do a reboot of what is the parent partition now, we have to shut down those virtual machines as well. Which actually leads us to an interesting point. So I said, hey, this is the same hypervisor that Azure uses. Yes. But then you do start to get some divergence when you look at things like how it handles these management functions. For example, in Azure, there's a technology called VMBus, Virtual Machine Preserving Host Update. And what that does is it lets you replace the parent partition without shutting down the virtual machines. Now, it pauses them, but the technology in Azure is very quick. It just pauses them for maybe 30 seconds. And that's one of the features Azure has implemented because of the large scale, because of the types of things they do, that we don't have in the on-premises Windows Server. Now, some of that is because the circumstances are different. On-premises, you're nearly always going to have things like failover clustering for your Hyper-V hosts, and I would just live migrate the virtual machines. So again, there's zero downtime to the VMs at all. In Azure, some things migrate now, but not everything. So this is a step better than having to restart when they have to do maintenance updates on essentially what are their hypervisor boxes. But there's innovation in both ways. The fact that it is the same hypervisor. For example, Windows Server 2025, well, they've introduced GPU partitioning. Now, I could always do discrete device assignments. So I'd actually map a device on the PCI slot into a particular virtual machine, but I couldn't share it. Now what we have in Windows Server 2025 Hyper-V is I can share GPUs, just like I can share a CPU, between multiple virtual machines. Azure doesn't have that today, but you can bet that GPU virtualization will find its way into Azure. I mentioned this virtual drivers, virtual service consumer, which talks to the kernel mode bus, which then goes and talks to the virtual service provider, goes through the I/O stack, talks to the drivers. So does that mean in the guests, they see a bunch of emulated hardware? Because that incurs a certain performance penalty. When I have to pretend that I'm a certain piece of hardware, there's always a performance penalty with emulation. The reality is most modern operating systems today are what we call enlightened. They understand they are a virtual machine. They understand, hey, I'm talking to a synthetic storage driver. I'm talking to a synthetic network card. I'm talking to a synthetic set of input-output, synthetic displays, a whole set of synthetic hardware. So it doesn't have to emulate that. And we can see this when we go and look at our hardware. So what I've done, I tried to make this as glaring as possible. So what I have over here is a Windows Server, I think it's a 2025. I'm looking at Device Manager. And then what I also installed, I was trying to be as bad as I could, I did a Windows 2008 R2. The reality is, even my Windows 2008 R2 has a whole bunch of synthetic things it understands. You can see over here, I tried my best, but there's still a Hyper-V keyboard. If I go and poke around my system devices, you'll still see a whole bunch of, hey, it understands a whole set of synthetic capabilities. But I did kind of fake it. If I look at the settings, I made it a Gen 1 virtual machine, so it has a BIOS. I also, because it's generation 1, and we're going to talk more about this in a second, it has an IDE controller. And I also added specifically a legacy network adapter. Even though I didn't even need to do this, I could have just used the regular network adapter. I kind of wanted to show you as much bad stuff as possible. And so now if we look at the properties, we can see, well, in this older OS that's a Gen 1 that I've kind of forced some older stuff, we see some emulated hardware. We see it has an Intel IDE controller. We see it has an Intel fast Ethernet adapter. Whereas if I look, and that's the only things I could get to be, again, even 2008 R2 can run basically all good stuff, but I made it a Gen 1. If I look at my newer OS on a Gen 2 virtual machine, well, it doesn't have a BIOS, it's UEFI. It just has a Hyper-V network adapter. It has a Hyper-V SCSI, so we're booting from SCSI, not IDE. It has Hyper-V input devices. It has Hyper-V display. It's fully enlightened. There's no emulated hardware going on here. It's all fully understanding. And that's exactly the same for Linux. Pretty much all of the major Linux distributions also fully support enlightenment, fully understand. Like if I grep for Hyper-V, they're just built in. I have not installed anything on this. So we can see the Hyper-V storage services, the network services. We can see the VMBus. And then you can see all of these things rely on the VMBus. So we can see all of those are going through that kernel mode capability. I could also go and look for what is my storage class. So what is it actually talking to? And you can see it's talking to the Microsoft virtual disk. So it's understanding fully, it's all talking to virtualized hardware. And again, I've installed nothing. This was just a straight Ubuntu ISO I downloaded and I installed it. So Windows, Linux, it doesn't matter. You get this fantastic, now just out the box, they're fully enlightened. And if we actually go and look at the docs for a second, I'll actually load up both pages. You can actually see for Windows, the supported guests. Now, the supported guests are really going to align with what is supported by the vendor. But we can see all the way back to sort of even Windows 2008, just install the latest updates. And you've got it. For 2012 and above, it's all just fully built in. For Linux, massive number of Linux distributions. And remember, there's obviously a lot of Linux distributions that are based off of these kind of core ones that we have over here. But if I was to go and look, CentOS is the first one, you can see built in. They're built in. As you look at all of the capabilities, all of these different features are just built in as part of Linux. I don't have to go and do anything special to make it work. I'm just going to get a fantastic experience because Microsoft did a whole bunch of work actually with and submit a lot of code to the Linux kernel to make it fully enlightened, to make it work fantastic and super cool performance with Hyper-V. Now, I used the term generation a couple of times. If you've played with Azure, you've already seen this because Azure, again, because it's built on Hyper-V, it has that concept of the generations of virtual machine. And there's two. So there's the Gen 1 and the Gen 2. The Gen 1 was BIOS-based. Now, because it was BIOS-based, it means you boot off of an IDE controller. I have to boot off of a legacy NIC. So a lot of the hardware, well, some of it is emulated. Some of the hardware is emulated. So you get this IDE, and if you want to boot, use a legacy NIC. If I'm Gen 2, it's UEFI based. This means I can get a virtual TPM. This means I can do secure boot. There is no virtualized hardware, no emulated hardware. It is all synthetic. That means I'm booting off of a SCSI controller. I can also Pixie boot off of just a regular network interface card. Now, reality is they even did work with the Gen 1. Once the integration services load, even for a Gen 1, it switches the path used. So the IDE controller works at a very similar performance as the SCSI controller. So if I'm using a Gen 2, it's going to boot a little bit quicker. It will install a little bit quicker. But overall, once it's booted, the performance will be the same. It's really about, hey, I get some of those more advanced capabilities. I'm removing that emulated hardware. I get the virtual TPM. I get secure boot. So as much as possible, we're going to want to use the Gen 2 into our environments if we can. And because the disk structure is different, BIOS versus UEFI has a different disk structure, it's not easy to convert a Gen 1 to a Gen 2 or a Gen 2 to a Gen 1 because the drivers are different, the disk structure is different. So generally try and get what you want first time. So let's dive into a bit more detail about each of these resources. And I want to start with CPU, because obviously a CPU is an interesting, it's a core one where we think about, hey, what are we doing at the processor level? Now, I want to start off thinking about what is the physical box. Now, we're used to the idea today is the physical box has a certain number of actual processors. Think of sockets. And today, everything is multi-core. So within the processor, there's a certain number of cores. I'm lazy. I'm going to say it's a 4-core processor. This is not realistic. Most server processors, they have way more cores than that. And then also, most of them today have hyperthreading. And what hyperthreading does is it duplicates certain components within the core. So instead of having to always wait for certain data before it can execute an instruction, it can very quickly execute another thread. It doesn't double the performance, but you get a certain amount of performance boost. And so then you split these again with the hyperthreading. And so in this scenario, if I look at this box, each physical socket, 4 cores hyperthreading, is 8 logical processors. So in total, this box would have 16 logical processors. And if I was to look at my actual server for a second, I don't actually know how many I've got in this box, but if we jumped over and looked at my box, let's actually minimize this and try and get some stuff off of our screen. If I look at Task Manager, nope, that was wrong. Look at Task Manager, look at my performance, and look at my CPU. In my case, I've just got one socket. That socket has 4 cores. It has hyper-threading. And so I have 8 logical processors. And it's telling me that virtualization is enabled on this. So what I have inside this is 8 logical processors. Great. So then our virtual machines, we allocate a certain number of virtual CPUs. So I drew the word CPU. That's not actually accurate. It gets a certain number of virtual CPUs, and I control how many I give it. So maybe I'll give this virtual machine 4 virtual CPUs. This one I'm going to give 2. Now, what I can absolutely do here is there used to be a ratio. Hey, based on the number of logical procs, you can only map that one logical proc to 8 virtual CPUs. That's gone now. I can really do whatever mapping I want. So even though I've only got 16 logical props, this is not a one-to-one mapping. I could have 2 logical processors, and I could allocate 20 virtual machines to each. I can't allocate more virtual CPUs than exist in the box, but I can absolutely overcommit. I could have 16 logical procs. I could create 20 virtual machines with 16 virtual CPUs each. Now realize it's not magic. I do that because the assumption is, well, the boxes are not actually running at 100% CPU. And I want to maximize the utilization of my resource. So by pooling the things together, hey, I might overcommit 4 times because I assume my average workload maybe runs at 25%. And so if I've got 16 logical procs, well, maybe I'd go and allocate 64 virtual CPUs across a bunch of virtual machines. If they all try to max out, they're going to be limited by the actual compute capability. So I get a choice of how much I want to overcommit. And there's actually a bunch of different things I can do, but they do not hard link. Like these 4 virtual CPUs do not always go to these 2 cores and these hyperthreads. It's dynamically allocating how it wants to assign those. The hypervisor slices up the CPU cycles and allocates accordingly. Now, one interesting thing when we think about scale, it's pretty big these days. So if I think about the physical box of what can be supported by Hyper-V, it's 2,048 logical processors and up to 4 petabytes of RAM, which is really kind of crazy numbers. In terms of what I can put inside the virtual machine, each virtual machine could see 2,048 virtual CPUs and up to 240 terabytes of RAM. So I can really just create some absolute monsters of virtual machines if I want to now. And obviously I can have these monster hosts. Most people are not running boxes this big, but Azure may. And so again, it's that investment being done in the hypervisor so that all of the different places Hyper-V is used, Windows Server, Azure Local, Azure can take advantage of these fantastic capabilities. Now, I can actually do a lot more than just allocate a certain number of virtual CPUs. Now, I cannot change the number of processors when the virtual machine is running, so I can't add, which is honestly not that useful because most operating system and most workloads will not dynamically understand if you added processors to it. So that's kind of set in stone before I start the virtual machine. But if I go and look at the settings of my virtual machine, now notice I'm going to look at my processors. So the number of processors is grayed out. I cannot change that. But what I can change is the reserve while it's running, the limit while it's running, and the relative weight while it's running. So think about what those three things right there are actually doing. So this will be the number of virtual CPUs it sees. Okay. This is saying I want to ensure, because remember, if multiple virtual machines all try and max out at the same time, they're now going to get contention for what physical amount of CPU capacity exists on the box. So what this lets me say is, hey, this VM, I want to make sure it always has this percentage of the processor I've allocated to it available. So maybe I'll set it to 25%. So it always has at least that available in times of contention. Obviously, I can't overcommit the reserves amounts of the physical box. Limit says this is the amount you're allowed to use. And you may say that's really kind of weird. Why would I have a limit? This can be used as a nice trick. I can't add processors. But what I absolutely could do, I could say, I'm going to give you 8 virtual CPUs. I don't want you to normally use that. So I'm going to set your limit to 50%. And that would mean, although you've got 8 virtual CPUs, you can really only use 4 virtual CPUs worth of compute. So I've limited you to 50%. Then if there was some reason I needed to let you do more processing for some reason, I can change this then to 75% or 100%. Let you do the job and then reduce it back to 50%. So this would essentially let me change the amount of compute you can do because the hypervisor is always telling it how much slice it's going to actually process and let it do work. Then the relative weight is really useful for, well, actually in this case, what I now do is I may have that contention, and rather than mess around limiting and changing percentages, hey, this is maybe a domain controller. This is my SQL database. If there's ever a contention, you have a higher weight. Maybe your weight is 400 compared to this is 100. You'll get 4 times the number of CPU slices than this one will. So it gives me a lot of power to modify exactly how that allocation will work. So I have a lot of control of what that's going to do. And there's been some really nice enhancements to the scheduler in Hyper-V. So one of the things they did in, I think it's Windows Server 2016, is they introduced a new core scheduler. And it used to be saying I would configure on Windows Server 2016, and that's the default in Windows Server 2019 and above. And it's about this idea of the hyper-threading. Because imagine if I'm not in a trusted environment. Now, in your premises, you may trust all your different workloads. It's not a big deal. In Azure, I don't trust the tenant next to me. So this idea of sharing a core with hyper-threading may be very unattractive. We've heard of side channel attacks, for example. So what the core scheduler now does, it will not allow processes from different VMs to be scheduled on the same core. It would ensure only processes are scheduled on a core from the same virtual machine. So I could never have 2 VMs trying to actually operate things on the same core. And we can see that if I jump over for a second and I go and look at, where's Event Viewer gone? Event Viewer. And I look for my event ID 2 for my hypervisor, I can see my hypervisor scheduler type is 3. 3 means it's using the core scheduler. 1 and 2 are the classic. And so I know, yes, I'm using that improved core scheduler. And that is both for Intel and AMD. So that is a really great capability. Now, another really common thing we're actually going to have happening here is I drew the idea of a host. Well, you're going to cluster them nearly all of the times in a production environment. I don't want a single box being my Hyper-V box because, again, during maintenance, I want to live migrate, and we'll talk about what that is. I want to live migrate VMs to another box, so there's no downtime to the guest whatsoever while I'm doing maintenance and reboot in this box. Things can fail. Well, if things fail, I want them to automatically start on another box. So we're nearly always going to cluster these. Now, ideally, all of the hosts in my cluster will have exactly the same hardware. But imagine the scenario, built my cluster, or maybe I'm migrating off of something else and I want to make the cluster bigger, and it's a year later or 2 years later. I can't get exactly the same processor. Things have advanced a bit. So now I've got a newer version of the processor. Well, the problem is newer versions of processors will generally add capabilities. They'll have expanded instruction sets. And what happens is when I'm a virtual machine, remember, I see the capabilities of the underlying processor. If I go and look inside a virtual machine, what I absolutely see, if I was looking at my host, look at Task Manager, I have a certain type of processor. So I see I've got an Intel Xeon, blah, 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 blah. If I look inside a guest, let's move this over for a second. If I go and look inside my guest virtual machine, and I look at my task manager, and look at my performance and my CPU, I see exactly the same processor. So they match, which is a good thing because I want my virtual machines to see and understand all of the capabilities so the applications inside can see that instruction set, use it, optimize its performance. But if I have my cluster, and then I go and add 2 new nodes that have a newer processor, and my VM starts on that newer box, sees the instructions, happy, 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 and then it gets live migrated, so the OS is not shutting down and starting again, to an older processor, and it tries to access that instruction that does not exist, it would be a very sad day. Now, there are flighting checks, it won't let you do that, but that would be a huge problem. So there's the ability to actually tell the processor to dumb itself down. Now there's 2 levels of this dumbing down. The one we used to only have was this idea of a processor compatibility mode. And if I go and again look at, I'll just go into Hyper-V Manager. And if I was to look at the settings of one of my virtual machines and we extend out processor, notice there's this compatibility. Now, I can't change this while it's running because what this is going to do is in its one format, it will dumb it down to a really, really lowest possible level. Now, I still can't migrate from Intel to AMD or AMD to Intel, but when I check this at its normal level, it dumbs and hides nearly all the instruction sets that are above the bare minimum. So I'm going to lose a lot, but obviously now I'd be able to move this virtual machine, live migrate it between anything that was Intel or anything that was AMD. It's hidden all of those higher instruction sets. So that's one capability that you have if you need that complete flexibility. But Windows Server 2016 introduced a dynamic compatibility mode. Now that's a feature of failover clustering. And what that will do is it would look across all of the nodes in my particular failover cluster and work out what the lowest common denominator was and only expose those. So instead of dumbing it down to a really low level, it will only dumb it down to enough to let you move between any of the nodes in that failover cluster. And if I leverage PowerShell, I can go and set those particular configurations and move that all around. But that's a fantastic capability if I do have that discrepancy in my failover cluster. I wouldn't want to have it at that really dumbed down level for long, because obviously I'm hiding instructions. I'm going to reduce the capability and maybe the application's performance inside that would use those instructions or the OS using those instructions. But it's there if maybe I was doing some certain sets of configuration. You probably also saw there was the NUMA configuration. So NUMA is all about their non-uniform memory access. I may have got that acronym wrong. But it's about the idea that when I have those physical sockets with the processor in it, well, there's also certain memory banks that are tied there as well. Why won't that go away? It's annoying. Go away. Come, there we go. And you see this NUMA node. Now, the NUMA node is automatically configured based on what it sees in the physical hardware. So it does map that through to the virtual machine, so the things inside the VM can make good cases. When it's shut down, I could change these topology if I had to. You typically won't. You typically only change that if I had maybe different NUMA topologies within a cluster. So again, I need to make something so if it did move between them, I'm not going to hit a problem. The other thing that Hyper-V does is if I go to the actual box configuration. No, that's not right. Maybe it's back up here. There we go. Is it enables NUMA spanning by default. So this is just enabled. And what that means is it's going to let you be able to map memory that isn't part of the same NUMA node as the processor. Basically, it means I can run more VMs at the same time. It's not restricted to only being able to map memory to the particular sockets. And you may get a little performance penalty. I mean, it's tiny, because now, again, processors are now talking cross to another socket where the memory is connected. But for most purposes, that's really not a big deal. So it's just enabled by default. But no, hey, you can tweak that if you really wanted to. Now let's talk about memory. So memory, obviously, I have a huge amount of physical memory. You cannot share memory pages. So if I have a particular memory page, let's say just over here, I have a page of memory. Well, two VMs can't map to the same memory page at the same time. We're not in the quantum world yet. I can't store two different values in the same bit of memory. So there's no memory sharing. There's no page sharing. Like, it doesn't do data deduplication. So if two VMs had the same content of a page of memory, it doesn't just save it once. The reality is nearly every OS uses large memory pages today. And so the chances of finding exact duplicates are not that high anyway. But it does not do that. If you really had this scenario of just a massive number of instances running exactly the same thing, I mean, maybe that's a scenario for containers. Like, containers virtualizes the OS. So virtual machines virtualize the hardware. Containers virtualize the operating system. So then they share the kernel, but then I can have lots of little sandboxes within an OS instance that are isolated at kind of the process, the network, the namespace. So that may be a better fit if you had that scenario of like tens and tens of exactly the same thing. Maybe containers is a better fit for you. So we're not sharing memory pages, but there are a whole bunch of memory technologies. The first one is dynamic memory. Now, if we go and look again at a virtual machine configuration, I'm not using dynamic memory for most of these. Like, if I look at the memory tab, you can see I've just assigned an amount of memory. It does actually know what the demand is. So it's actually not using most of it, but I disabled dynamic memory. But on this one, so go and look at the settings. It's not running right now. I enabled dynamic memory. And what dynamic memory lets you do is you can set a minimum amount it can ever have. You can set a maximum amount it can ever have. When I use dynamic memory, the amount I specify here becomes the starting amount. And then I can set a buffer, i.e., don't let it just drop to 0, then add memory. I always want it to have 20% available inside the guest. So go and add memory into it as you need to. And also, I can then set a weight for how important this memory is compared to other virtual machines. Now, once I start this virtual machine, if we now go and look at the settings, I cannot change the starting amount, but I could reduce the minimum. I can't increase it. And I could increase the maximum. So I can change those values, and I can change the amount of buffer I want it to have. So this is a really nice, if I had workloads, maybe I am kind of overcommitting, I had lots of things, virtual desktop environments would be great for this. This lets me adjust the amount of memory inside the operating system, depending on how much it actually needs. Like if I looked at this one right now, the assigned memory is 4096 because that's the amount it started with. But it could reduce it down to 1 gig. It could increase it up to 8 gigs, depending on the load inside of it. I'm just going to shut that down, turn off. Now, the way this is actually doing, and something to be aware of, when you create a virtual machine like this, I think the default is 1 terabyte is the maximum. I would change it off of that. Realize some processes inside an OS will look at what memory there is and just start using it. So never leave the default as like this massive amount of memory. I would change it to something sensible. Realize this won't work well for some things. If I have something with a caching component, that caching component might just try and allocate all of the RAM it can see. So dynamic memory would not be a good fit there because it would just see the maximum and just try and use it all. So it would always grow to that maximum amount. Now, one thing you may be wondering about is how do you take memory from a regular operating system? Like maybe I could do hot add, but hot remove is a very difficult thing. So imagine I had these memory pages, let's just say 5, and they've been mapped into this virtual machine. Now, because of memory pressure and it's not using it or something else needs it more, Hyper-V wants to claim, let's say, 2 of the pages back. When we saw Linux, you probably saw that balloon driver thing. So this is a kernel mode device driver that is inside Windows, inside Linux. If Hyper-V needs to claim some memory back, what it does is it inflates that balloon driver. So that balloon driver says, I need this amount of memory, 2 pages worth. Obviously, it would be a lot more than that. Because it's a kernel mode device driver, the OS has to give it to it. It has to find it. It could be paging away stuff, doesn't matter. It has to give it that memory. So now, once this balloon driver has been inflated and it's been allocated these 2 pages inside the guest, well, now nothing else can use it, only the balloon driver. What this now means is Hyper-V knows these 2 pages can no longer be used by the guest, so it can take them and allocate it to another virtual machine instead. Now it might say, oh, okay, well, those 2, now I'll go and give it and add it into this one. If this now had memory pressure, well, it may deflate the driver and then allocate some new pages to go into there. So that's one of the ways that it can actually take memory back is via that balloon driver. So that's really good when you have these dynamic workloads. VDI can be a really nice use case for that. So that's one of the things that does. Now there is another option. If we go back over and look here, for this virtual machine, if I look at the settings again, I don't have dynamic memory and it's running, but it will let me change the value. So this is called runtime memory resize. Now I can't use this and dynamic memory. It's one or the other. This is not dynamic. This would be me making the choice. I want to add memory into this virtual machine, but I can change this value. Now this only works with clients, the Windows 10 or above, Windows Server 2016 or above, Linux that have the hot add capability. And here I am specifically going in and I want to change the amount of memory it has. And then once I changed it and clicked OK, it would now just show up in the OS. Remember, the OS is completely enlightened. It understands it's not really running on physical hardware. It understands they're not real pages of memory that it has. And so that's why it needs that guest support to let it go and add and take pages back, which is that runtime memory resize capability. So I do have a number of technologies that I can use for memory. Yes, I have the balloon driver, which is great where I want the hypervisor to dynamically change the memory based on the demand. Then I have the runtime memory resize when I, as the admin, want to specifically add or remove memory based on some particular event that I know is happening. So now, that was the CPU and memory. What about the network side? So we have virtual network interfaces. We saw there's the synthetic network adapter and then that legacy emulated network adapter. You're pretty much always going to use the synthetic network adapter in pretty much any OS today. I can have multiple NICs attached to a virtual machine, which can go and map to different things. And in terms of what they map to, well, if we go and look at what's available for us on our host, if I look at my Hyper-V box over here, we have our virtual switch manager. And notice there are 3 types. I can create external, internal, and private. Now, what I'm doing on all 3 of mine that are running is connecting to an internal, which when I explain what they are is not going to make sense since all 3 of them can access the internet. But I'll expand on that in a second. So I can create multiple switches, and then within the actual virtual machine, for each of the network interfaces, I map it to a particular virtual switch. I can turn on VLANs if I want to. I can do bandwidth management to ensure a minimum and a maximum amount. There's a whole bunch of other features I have available, really rich capabilities there. But what we're doing, those three types. So imagine I think of the idea, what colors did I use up here? Purple and blue. Okay. So I have the parent. So I have the parent. That's not how you spell a P. I can cheat. Parent. And the child. One or more child VMs. These are virtual machines. So in the parent, obviously, I have a physical NIC or more. I can have multiple physical NICs. Now, what typically we'll do is we'll use NIC teaming inside the parent, so they're resilient to any kind of network interface or switch failure. But I have a NIC. And one of the types I can create is called external, which makes sense. This type of virtual switch connects to a physical NIC on the host, which then has some external connectivity. So it's a way of giving the child VMs access to external networks. But I can also create something called internal. So internal, you get this idea of a virtual NIC does get created in the parent as well, but it's not mapped to a physical one. And then obviously I can attach virtual NICs to externals or internals. This enables connectivity between VMs on the same host and the host itself. Now you may at this point say, well, John, you are using that on your one, but my VMs can all access the internet. On my parent, I actually set up NAT, a NAT gateway, and a DHCP server. So my parent is actually acting as a NAT gateway. So although the child's only talk to the host then goes and talks to the internet on their behalf because of the way I'm running my Hyper-V host. And then the other type is private. So with private, the host can't see it. This would just be, hey, VMs connected to the same private vSwitch could talk to each other over it. So I have those three different options for that connectivity. Now, as we saw on the screen, if we jump back over, we do have that ability to use VLANs. That's a capability right there. We do have that bandwidth management. I can also turn on various hardware acceleration. So virtual machine queues. Now this does require the NIC to support that. That provides separate receive and transmit queues that, depending on how many VM queues are supported in the NIC, they get allocated dynamically across the VMs. They get spread over different cores. It can use dynamic capabilities to directly pass packets into the virtual machine memory as well. So it's all reducing the latency, increases performance by spreading the load over multiple cores, and it gives me a better performance. The other things I can do here is, yes, IPsec task offloading, but if my network card and my motherboard support virtual functions, I can turn on SR-IOV. And what this now does is it bypasses the virtual switch completely. A virtual function from the network interface card gets mapped into the virtual machine. And so now it's the lowest possible latency you can get. And then there are other advanced features. You can see here things like MAC address spoofing, so I can pretend I'm something else. I can protect against DHCP fake kind of servers, root regards, protecting. There's a whole set of capabilities I can do. So there's a lot of different things beyond the scope of what I want to try and cover in this particular video. But suffice to say, there's a lot of different networking things that I can do here. And realize this is just basic stuff. I can also do software-defined networking. So the same things we do in Azure with the virtual networks, and we can do. We're going to leverage System Center Virtual Machine Manager really to act as the management plane. But then I can define blue, green, red networks. They're completely abstracted from what the physical network structure is. I think it's using VXLAN today. They enhance the technologies. But I get a lot of really nice capabilities there. On the storage side, I'm not going to cover the GPU, but I can virtualize the GPU as well. Typically, we're going to use the VHDX format. So VHDX is the NUMA. There's also VHD. There's three types. There's dynamic, where the disk starts off very small, and it grows as I write data to the disk. There's fixed, where it allocates all of the space up front, and then there's differencing. So differencing, hey, I have a parent disk, and then I only want to save the changes from the parent. That's, again, useful for like VDI scenarios, or where I have lots and lots of copies of a particular disk, and I want to try and optimize my amount of space. So there's 3 different types here. Now, in terms of where these live, I mean, they can live on local storage. Again, if I'm clustering, I don't want to put it on a local disk. I could use storage spaces direct, so it's hyper-converged. So clustering uses SMB3 to replicate and make the volumes available as if it was a cluster shared volume, even though it's local storage across the nodes within the cluster. I could have a SAN connection via iSCSI or fiber channel. I could be using an SMB3 file share. I have whole sets of choice on where I store them. I mean, I can dynamically resize these disks. I can add and remove from running virtual machines. I do want to use VHDX as much as possible. Remember, the point of virtualization is I'm abstracting the physical world from what the virtual machine says. So I've got lots of good mobility, for example. But if required, I could actually do things like virtual fiber channel. I can map virtual fiber channel adapters into my VM, which map to physical host bus adapters in the host, and then connect directly from the VMs into a SAN. I could obviously use iSCSI, which is going over the network connection. And typically we do that because maybe we want to have a shared set of storage between the VMs. Well, I can do shared VHDX. So with shared VHDX, well, I can connect multiple virtual machines to the same file, and then it will be seen as a shared volume. I can do SCSI persistent reservations, all of that good stuff on it. Another thing we may want to do is actually move storage. So, hey, I'm connecting to this VHDX file and it's sitting locally, or it's on a SAN and I want to move it to a different SAN or an SMB file share. You can do a live storage migration or live storage move. So imagine I have my Hyper-V host and I've got my VM. And then I've got 2 different SANs. We just say it's SANs, but it doesn't matter. Maybe it's a SAN, and maybe there's an SMB3 file share. I want to move it to whatever. So today the VHDX file is sitting here, but the VM is running. So right now it's mapped and it's connecting through this way. What live storage move will let me do is it will start copying the data into here. As writes occur, it will also write them into this one, so it's kept up to date. And then at a certain point when it's ready, it will just flip it. So now this becomes the path, and I can get rid of that one. So it gives me complete mobility of where the storage lives without any impact on the virtual machine itself. Now, I guess when we talk about mobility of the storage, realize there's mobility, and I mentioned live migration in the past before. There's mobility of the VM as well. In fact, I might as well take the same picture. So in the virtual machine world, if I think about, well, I have another host here, and I want to move the virtual machine, what it will actually do is it will create a new VM over here. It will start copying the memory. Now it's still running. So it's copying the memory, but the pages are changing as it's copying it. So it does a pass, then it has to go back and do a smaller pass because it changes the dirty pages, the ones that have changed since the copy. Well, that takes some time. So it has to go back, some more pages are dirty, so it has to do it again. But now it's a lot smaller. And it gets to a point it's so small, well, now it will pause this virtual machine, copy over the remaining memory, the CPU state, the GPU state, all of those things. And now it can just start this virtual machine. That one gets shut down. It will do a reverse ARP, so clients get redirected to it. And we're good to go. And I have complete control over that. Like I can set which networks to use with that. I can set things like, well, how many concurrent Live migrations, that's on the Hyper-V settings. Do I want to do live migrations? How many do you want to enable simultaneously? In a cluster, you typically have a separate network used for this, but I could say I want to use a specific IPs, networks for this. I can control how many storage migrations I want to be happening simultaneously. There's replication as well. So I have something called Hyper-V replica for DR scenarios. There's even a combination of these two things. So I could move virtual machines. So if I do move, I get to pick, is it moving the VM or its storage or just the VM storage? It doesn't even have to be clustered. It doesn't have to have any shared storage. So I can do a combination of a shared nothing live migration, which does both of these. Imagine the VM was running on this box using local storage. Well, it will do a storage move and a live migration together to move all of it to a completely different environment. So maybe it's from a standalone host to a cluster to a different cluster, whatever I want to do here. I have a huge amount of flexibility when I think of the migration, the capabilities that I actually want to leverage there. I know this is maybe a longer video than I originally intended, which is always the case for anything I do. You should be used to it by now. The other thing I would just really quickly mention from a management perspective, now what you've seen me use a lot here was Hyper-V Manager. So if I jump over, and Hyper-V Manager is nice, and there's PowerShell, commandlets. It's nice for a fairly small environment. Like I could actually add multiple servers here. I could add another server, and I can manage the things through here. Again, I can use PowerShell scripts to do a whole bunch of stuff. Obviously, Windows Admin Center is free. That's really nice, and that can hook into, obviously, all the clustering. I can see all my VMs here. I can do all my config here. Got my VMs. I would see all of the different aspects of this. Again, failover clustering adds a bunch of functionality that I'm going to want to be using as part of this. So Windows Admin Center might be nice if I'm maybe more cost conscious, or it's, again, a small environment. For a large environment, though, you probably really are looking at System Center Virtual Machine Manager. That's the enterprise management solution for Hyper-V based environments. I'd probably want to use that. I can Arc enable all of this, and that's completely optional. Then obviously it brings the Azure control plane and some of the Azure services to this. And I can run Arc on the Hyper-V servers. I can run Arc with SCVMM. It just kind of bolsters all of that up. So you may be wondering, well, okay, well, how do I get this? There is no free version. There used to be a Hyper-V server that primarily I would use for sort of VDI and Linux only environments. Today, I'm buying a license. I'm either buying the license by buying Windows Server cores, which most environments and customers own. So it's not an additional cost. They have it already. Or obviously, I can use it through things like Azure Local. With Azure Local, I pay as part of the Azure Local solution to give me that Hyper-V hypervisor. But those are really the ways that I'm getting Hyper-V. It's either, hey, I'm running it via Windows Server, so I'm licensing Windows Server, or I'm using Azure Local, what was Azure Stack, HCI, etc., etc. So that was my quick overview. I mean, really my key points I wanted to kind of stress was it is a true Type 1 hypervisor, just like VMware or KVM, whatever else is out there. It's got some really cool technologies around the memory management and the CPU capabilities. It is microkernelized, so it has huge support for hardware, so it doesn't try and cram the drivers into the same partition as the hypervisor. It's built in to pretty much all Windows, all Linux distributions out there, so I have a huge flexibility in my guest operating systems. There's a lot of fantastic technologies been added around sort of the network capabilities, software-defined networking, storage, replication, live migrations, shared nothing live migrations. And then I have a whole set of capabilities in terms of the management. And of course, I can Arc enable all of this if I want to. So I hope that was useful. As always, till next video, cheers.